Well, as you probably understood from the thumbnail, I'm going to show you why all of the angles in a regular pentagon must be equal by using this circle theorem, the one that says angles in the same segment are equal. And I'm going to use a basic concept from this theorem. Firstly, I'm going to point out what we need to be looking for that will help us get the angles in the regular pentagon. The shape is made of two straight lines that intersect, and the ends of each line are joined by one straight line. And the shape looks a little bit like a butterfly. With this shape, one interesting result you get is that angles pointing in the same direction have the same value. So the blue angles have the same value, and the bottom two angles, the ones colored red, because they're pointing in the same direction, they have the same value. I've made a previous video explaining exactly why these properties exist, and it's linked in the description of this video. And feel free to check out that video to understand exactly how this works. And now let's begin with a pentagon that has none of its angles marked yet. Now the first thing I want to point out is that all regular polygons, including the regular pentagon, are cyclic, which means that you can always find a circle of a certain size so that each vertex of the polygon will sit on the edge of the circle. So let's add in this circle, and as you can see, every vertex lies on the edge of this circle. Also, bear in mind that because this is a regular polygon, all of its edges are of equal length. The first thing I'm going to do is draw a line from one vertex to another. We'll choose the horizontal line. This line divides the pentagon into two shapes, and the top shape is a triangle. But the left and right edges of the triangle are also the edges of the pentagon, and because it's a regular pentagon, those two edges are the same length, and so this must be an isosceles triangle, and so the base angles must have the same value. I'm going to label both of the angles with an A. Now I'm going to choose two other vertices and connect them with a straight line. Now if you look carefully, you should be able to see that this has created another isosceles triangle on the right. I'll highlight it. The left and right edges of this triangle are the edges of the regular pentagon, so they must be the same length, and that means their base angles have to be the same. But this line that we just drew intersects with the first line, and that creates the shape that we discussed earlier. Now each vertex of this shape is touching the circle, and it's exactly the same shape that we discussed, which means the angles pointing in the same direction must have the same value, and that must mean that this angle on the bottom must have the value of A. But because the bottom angle A belongs to this isosceles triangle, the other angle adjacent to the base must also have the value of A. By continuing to add lines in this way, we're going to find most of the angles in the pentagon, and then we can show how each of the 5 angles in the pentagon are the same. So I'm going to add a third straight line between this vertex and this vertex, and by now you should recognize that because of these two lines we've created an isosceles triangle because the non-base edges are the same length. But this new line intersects with the first line, and again that creates the circle theorem shape. And we know that angles pointing in the same direction are the same, so this bottom angle must be the same as this bottom angle, so its value has to be A. And since this is a base angle within an isosceles triangle, the other angle adjacent to the base must have the value of A. And by now you know what we're going to do next. Yes, we're going to add another line between two vertices. Again, this creates an isosceles triangle, so these two angles must have the same value. But the newest line intersects with another, creating the shape from the circle theorem, and the angles pointing in the same direction have the same value, so this angle has to have the value of A, and because it's a base angle within an isosceles triangle, the other base angle also has the value of A. We'll now join the last two vertices. Of course, it's an isosceles triangle, which means these two angles have the same value. The new line intersects with two different lines, so there are two shapes we can use. We'll choose this one, and of two the angles pointing in the same direction, one of them is A, so the other one must be A. And because this is one of the base angles in the isosceles triangle, the other base angle must have the value of A. And we've done most of the angle labeling. Now here are the missing angles, and you should notice that each of the pentagon angles are just composite angles made up of 3 different angles, where the unknown angle is the one that sits between two angles of value A. We can find the value of this missing angle by noticing that it sits within a triangle. We can see that the sum of known angles in this triangle must be 4a, which means the value of the missing angle must be 180 degrees minus 4a. But this must be true of all of the missing angles, because they're all within triangles where the sum of known angles is 4a. It has to be true for this one because the known values are 4a. The same with this one, the known angles are 4a. So the missing angle has to be 180 minus 4a. It's true of this one as well, and it's true of this angle. And since all of the missing angles have the same value, and they are all part of a composite angle where the other two angles have a value of 2a, all of the composite angles have the same value, and therefore all of the angles in a regular pentagon must have the same value. Here's a quick quiz. Can you tell me the value of a in degrees? If you can, put it in the comments, and first correct comment gets pinned. Well, that's our proof for now. Thanks for watching.